In this lecture, we're going to look at some more explanations of logic in general and get into how to employ logic in MATLAB. So we're going to look at algorithms with decisions. We're going to look at how to write an algorithm that utilizes decision pathways that are when it's applicable to solving an engineering problem. We're going to look at the flowcharts to implement these decisions, and we're going to generate an approximate set of test conditions for all possible pathways. So we want to make sure we test what if it's true, what if it's false. So some of the motivation behind conditional statements are you want to give computers the ability to ask questions to take different actions based on the answers. But computers can only make decisions based on binary arguments, so they can only make a decision if it's true or false, yes or no, 1 or 0. It's the only way they can think. So just like in Excel, MATLAB, we can ask yes/no questions and conditionally execute code based on the outcome, just how in our if statements we said if it's true, do this. So with MATLAB, if it's true, we can run this piece of code. So we're going to look back at our flow chart. So before we had directional arrows, which showed the flow, and we had rectangles, which were the actions. Now we're going to add in diamonds, which are decisions. So these are where our yes/no questions take place. So to compare everything with Excel, in Excel we had a single if statement which had 3 parts. It was the question, true, or false. And we have our diamonds. We're asking our question, if it's true, we'll go this way. If it's false, we'll go this way. With our nested if statements, we had here's our question. If it's true, we'll go this way. If it's false, we'll ask our second question, if it's true or if it's false. So when you generate these type of questions, you want to make sure that both branches work. So you want to make sure you have a test case for if it's true, and you want to make sure you have a test case for if it's false. And if you have nested if statements, you must make sure you're testing if question 1 is true, if question 1 is false, if question 2 is true, and if question 2 is false. So you always want to make sure that you're achieving all of the outcomes that are possible in your decision tree. So let's revisit our example here where we're trying to determine the solid, liquid, and gas regions of our phase. We want to determine our algorithm and how this is really going to work. So the problem we are trying to solve is what phase is our material based on its temperature. Our knowns are inputs in temperature, which is going to be in degrees Fahrenheit by the user. Our output is the phase we want text. Other variables that we're going to need are the limits between solid and liquid. We're going to make the assumption that the pressure is 1 atm because that's what sets our solid and liquid transitions. So if we look at a written algorithm, how this might work is we ask the user to input a temperature in degrees Fahrenheit. We then convert that temperature to degrees Celsius. Then we set our solid and liquid limits, and then we ask, is our temperature less than the solid limit? If it's yes, it's solid. If it's no, we're going to go on. Then we're going to ask, is it above the liquid limit? If it's yes, then it's a gas. If it's no, it's a liquid. If we want to look at this in a visual sense, we can start where we input our temperature, we convert it to degrees Celsius, we have our upper and lower limits. We ask our first question, is it less than the solid limit? If yes, it's solid, which we would then proceed to end. If no, we ask our second question where we find out, is it greater than the liquid limit? If yes, it's a gas, and we can proceed to end. If no, it's a liquid, and we'll proceed to end. So for our test cases, we would want to test something where it's solid, where it's liquid, and where it's gas to make sure that all 3 regions of our decision-making algorithm are working. So if we want to look at another example, we're trying to classify our blood pressure, whether or not it is high or low. So we're going to develop a code to run this where we're going to ask the user to input their measured readings. So what do we know? Well, what we know is that we're going to get the age of the user, their systolic blood pressure, and their diastolic blood pressure, and the output result is text. We want to see if they're within the normal range or not. Other variables that we're going to need are for our age range to be able to figure out, are they within the min and max range for our 15 to 19 range or our 20 to 24 range. And then we're going to need our maximum pressure limits for our systolic and diastolic blood pressure based on the age ranges. So we're going to make the assumption that the user is between 15 and 24 years old, because otherwise we don't really have anything to do. So the first thing we might want to do is set all of our limits. So we have our age mins, our age maxes for our two ranges, and we have our blood pressure maxes for our two ranges. The second thing we can do is ask the user to enter their age. After the user enters their age, we can ask them, is their age less than the minimum or larger than the maximum? Because if it is, we don't want to use any of this code. If it's not, we can go on. So we really want to rule out whether or not they were within our age range at the very beginning. If they are within our age range, we can then ask the user to enter their systolic blood pressure and then their diastolic blood pressure. And then we have to figure out what range they are in. So we're going to ask if the user is less than the minimum for the second age range. If that's yes, that means they are in the first age range, and we can then ask, is their systolic greater than the max? If their systolic is greater than the max, we're going to report the result that they have high blood pressure. If not, we're then going to look at the diastolic, which if it is high, we're going to say they have high blood pressure. And again, if it's no, we're going to say they have normal blood pressure. If they had not been less than the minimum for the second age range to begin with, they would fail this. We would never trigger any of these questions. We would go straight to step 7, which then asks if their systolic is greater than the maximum for the second age range, and then it would ask if their diastolic is greater than the second age range, depending on the answer to the first one. So again, you would need to check for all of the cases in this, which is an age range lower than what is required, an age range higher than what is required, an age range in the lower half with high blood pressure in either systolic or diastolic. So there's 3 test cases for that, and then an age range in the second one with higher normal or regular blood pressure in the second range. So you actually need 8 test cases for this program to make sure everything is running correctly. So let's go on to look at rational and logical operators again. We want to ask questions in MATLAB using rational operators to combine rational questions with logical operators. We want to understand the difference between a short circuit and an element-wise logical operator. So our rational operators in MATLAB are still the greater than sign, the less than sign, the greater than or equal to sign, the less than or equal to sign. The ones that are different from Excel are primarily the equal to sign, because if we remember, the equal to sign is used in MATLAB to assign values to variables. So saying A equals B is going to assign the value of B to A. So it's not really, you can't use it for logic. So the way around that is you use 2 equal signs for logic. So you say A is equal B for a logic statement, and then the not equal to is different. In Excel, it was less than greater than. In MATLAB, it's squiggly equals. So let's ask some rational questions using scalars. So note that in each example below, the expression evaluates true, which is 1, or false, which is 0. So is A greater than 42? I can say A greater than 42. It's going to look at my value of A and tell me whether or not A is greater than 42. Is B less than or equal to 100? I can say B less than or equal to 100. Is C equal to the square root of D? So I can say is C equal D squared, D squared, not square root of D. Again, I'm using the 2 equal signs to denote equality. Is V less than the volume of a sphere with a radius of 6.72? I want to say is V less than 4/3 pi times 6.72 cubed. So you can put equations on either side. I can say is D different from the area of a rectangle with the sides of L1 and L2? So I can say is D not equal to L1 times L2 to get the area of that square. So this is how logic works with scalars. It's fairly straightforward in how you would expect it to behave. Now, how does it work with matrices? So assume we have these matrices defined in MATLAB. What we can do is we can ask, is x less than 1? What it is going to do is it's going to ask if each element in x is less than 1. So the result we're going to get is 0, 1, 1, 0, because you get a 0 if it's false and a 1 if it's true. So 2 is not less than 1, so it puts in a 0. So it's going to perform this logical operation on every element of these variables. So I say, is the second row of z less than or equal to x? I can say z, row 2, all columns, less than or equal to x. And again, you're going to get the results for what values are false and what values are true. Is y equal to the transpose of y? So y equals transpose of y. You're going to get which results are right and which ones are wrong. Note that the ones that are testing positive are the diagonal, which is what is true when you transpose a matrix. I can ask, is x greater than or equal to y? What's going to happen is you're going to get an error because x and y are not the same dimensions. You're trying to compare a 1 by 4 to a 2 by 2, so the matrix dimensions are not going to agree, or one must be a scalar. So just like when we're trying to do multiplication or division on vectors that are not the same length, you're going to get the same error when you're trying to logically compare them. So a few special notes: the operators less than or equal and greater than or equal must be written as two symbols. So you do less than equals, greater than equals. If you manage to type a single symbol such as greater than or equal to into a command, you will get an error because they don't understand what that input character is. To ask if two things are equal, again, you have to use two equal signs. It's necessary to differentiate from the assignment operator, which is the equal sign in MATLAB. It's how we just differentiate from saying A is equal to B by assigning the value of B to the variable A, and saying A equals B, we're going to compare if the two variables are equal to each other. MATLAB still has the same logical operators that Excel had. So in Excel we had our and, or, and not functions. In MATLAB, and is two ampersands next to each other, or is two vertical lines, and not is the squiggly tilde. The behavior works the same as it does in Excel. So for and, it returns true if all are true, or returns true if only one is true. Not inverts your logic. So a shortcut logical operators are denoted by two ampersands and two pipes. These are your and or. The operators only work with scalars, so you cannot use these with vectors or matrices. If the value on the left side of the and is false, the value on the right side is not evaluated, since the overall expression must be false. If the value on the left of your or statement is true, the value on the right is not evaluated, since the overall expression must be true. So let's take a look at this. We're trying to figure out the value of our resistance if it's not within 1% of the specified value. So we have the left side of the or statement and the right side of the or statement. So first it asks if Rx is less than 9.9 times RO, or Rx is greater than 1.01 times RO. So what it does is first it's going to check if Rx is low. If Rx is low, the second question is never asked because your or statement has already been satisfied. So although parentheses aren't necessary in these cases due to the priority of the operators, it's sometimes desirable to add the unneeded parentheses so you can visually see what you are comparing. If Rx and Ro are not both scalars, you will get an error because these variables will not work. So those were the double ampersand and the double pipe. A single ampersand or a single pipe perform element-wise and or operations. So these are the ones that work on vectors and matrices. The values being evaluated may be matrices, but they must be the same size unless one is a scalar. The result is an equal size matrix containing ones and zeros. So just how we are asking if two vectors were equal, we can now do use the and or symbols to further our logic. So the functions and or behave basically the same manner as x and y or x line y. So there are and or functions also in MATLAB to use. For logical comparisons, all non-zero values are assumed true, so only 0 is considered false. So let's look at this case. We have our two matrices defined, x and z. So we want to figure out which of the values of z are between -5 and 3 inclusive. So I can ask what values of z are greater than or equal to -5, and what values of z are less than or equal to 3. So the result that you're going to get is 0, 1, 1, 0, 1, 1, 1, 0. when it asks which of the values in X are greater than the corresponding values of the first row of Z or less than the corresponding values of the second row of Z. So I can say which values of X are greater than the first row in all those columns or less than the second row in all of those columns. Your matrix dimensions must agree, or one must be a scalar in order for you to use this element-wise type calculation. Just when we're doing multiplication and division, if you have different number of elements, it can't perform an element-wise calculation. So this is logical variables and how some of the functions work. In the next lecture, we're going to look at the if statements and how they perform in Excel to trigger what lines of code can be run. In this case, we're comparing variables.